Okay, so yesterday we have discussed a general overview of this industry, mineral processing and coal preparation. Now we are trying to get into the specific topics related to that. Now we have realized that to process my coal or mineral, I have to have first the understanding of what is that I am going to process, what are the basic characteristics. And I said that basically we try to separate particles based on physical properties. So what are those? How do I get to know? All this we are going to discuss here, some of them. I cannot cover everything. So it is the particle characterization, and this is what I advise everyone now. Measure properties, don't perform rituals. Why I am saying that? Because many industries still they believe in rituals, not the measurements. Okay, well, they think that measurement is costly, but I advise that you go for measurements. Okay. Now, you know what is this particle technology about? Yesterday you have seen that different people are having different opinion about your fine and ultra fine particles. It covers everything, whatever they say. Okay? There are many other areas also related to particle technology. So, particle technology is devoted to the understanding of particle and particle fluid interactions. Okay? And using the knowledge of properly designed processes and products. Even your say your CD drives, they are also having a particulate coating. Okay. The many places, okay, so we are living with the particles. Okay. So there is no need to extend that. So it is the properties of particle that dictate these interactions. That is a very, very important comment here, that who controls the particle fluid or particle interactions. It is the basically the particles, the properties of the particles that dictate these interactions. So particle characterization is at the heart of particle technology. Why I am saying that? Why not fluid dictates that? That I will explain. Now you know that for fluid, the properties are mostly known. They are documented in standard handbooks. We can easily tell you by looking at a handbook that what is the density of water at 40 degrees centigrade, or what is the viscosity of water at 40 degrees centigrade, or some other fluids we can look at. But can I tell, looking at a particle, what is the density of it? What is the surface area of it? What is the roughness of that surface? Can we tell what is the actually size of that particle? No, it is not documented. Even if you pick up two particles from the same place, they may be having differing in properties. So that is the difficulty with the particle. So if you think that fluid mechanics is very difficult and particle mechanics is easy, I would say fluid mechanics is much more established, fluid properties are much more established facts, not the particulates. So particle say actually the solid mechanics is much more difficult for understanding, because you have to measure the properties, you cannot guess. Okay. So the discrete nature of a particulate system means that it is heterogeneous. Very difficult to get a homogeneous particle mixture, specifically for mined ores, you will never get. Okay. Two particles in the same system don't have the same properties. So how do I know that what is the general behavior of my bulk material? I keep on saying that we deal with thousands of tons per hour. So how do I know what is the average property? Because when it is a heterogeneous mixture, how do I know their properties and all this? I cannot measure a single particle. Okay. So there what representative sample you are taking. How do you take the representative sample that must represent the entire population? Because even for particle characterization, you need a small amount of sample. So, that I am going to talk in my next lecture, that is how do I do sampling. So, sampling is a major issue, okay, which is being neglected in most of the cases. The properties of particulate system can't be tabulated like the thermodynamic properties of fluids can. Can you tabulate? The properties, say your heat transfer through a particle, what is the conductivity of that, or say actually we can no way tell that what are the different properties of a particle unless and until we measure. The properties of the system depend not only on the chemical composition, but also the particle morphology. I will explain what does it mean. Okay. I am giving this example, the surface area of sand. I give you 100 grams of sand. I ask you that what is the surface area of the sand? Can you tell? Even by doing lots of mathematics, you cannot tell. You have to measure it. Okay. But if I give you 1 kilogram of a fluid and if I ask you that what are the properties of that, probably you can look at that. What is the fluid you have to just identify? Probably they are documented in thermodynamics in your handbooks. Okay. You can get that. The properties are not always easy to define even. That is the most difficult problem for particles. How do I define that property? One good example is the particle size. I will get into that. What do you mean by a size of a particle? So, historically many particle properties have been difficult and time consuming to measure. And these challenges have led many practicing engineers and technologists to perform rituals rather than measure properties. They think that it is too costly, too time consuming and all this. So, they use some guesswork, that is the rituals means. But now the technology has been advanced, there are tools available, and if you want to have a tailor-made technology to be developed, you have to measure. Okay. There are tools available, some of them I will discuss. Okay. So, these rituals measure some empirical parameters. Hope you understand what do you mean by empirical parameters. Empirical means is a input output correlation without knowing what is happening inside. It is just a correlation. So, you may miss some of the important characteristic of that material if you go by the empirical parameters. Okay. So, but involve tests that can be easily and routinely performed. Okay. Such rituals are enshrined in company and industry standards. The need for these rituals gone to some extent. Okay. Effective online and offline measurement of real properties is now possible, like your today in many plants we are having online monitoring systems like your online particle size analysis. We are using image processing technology. I am just giving an example. Online the measurement of your flow rates and your mineral processing, even coal processing plants, you will find that you are having a control room now. 50 years back nobody thought that there will be a control room for a washery, but now we cannot think without that. We have a control room. So, control means you need the data. What is the data? That means you are measuring. So, the measurement tools are available. Okay. Now let me tell you that what are the difficulties in that. Very common, we all use this size, particle size, but now you see still we are going to the moon and we are doing so many missions and all this, and you see that even for the very basic where we are, basic definitions, particle size. Okay. So, what is the size? Size is the single most important property of a particle. Why? The particle size strongly influences other important particle properties, like your say fine particles are cohesive because surface forces, because when it becomes finer and finer. So, there are two types of forces, body forces and your basically the cohesive forces. Basically here what happens, the fine particles are cohesive because surface forces dominate of body forces. So, the particle property changes even with the size, what kind of forces will be dominant and all this. That is why I said that particle fluid interaction is basically dictated by particle properties, not the fluid properties in most of the cases. Okay. So, knowledge of the particle size of a system is essential, okay, and this controls the balance between surface forces and body forces, with the surface forces becoming increasingly dominant as size becomes small. Now, you tell me, suppose I give you a particle like this, what is the size of this particle? Can anyone tell? Very difficult. There is no concrete definition for that. For regular shape, yes, we can say, but for irregular shape, that is what we normally encounter in mined product. In naturally occurring minerals, we get this. Now, you see that where we are, there are many definitions proposed. When for a single property you have many definitions, you must be sure that there is some ambiguities in that. We should have only single definition if we are very sure about that. Now, what are these definitions? Sphere of same minimum length, that means I will get the volume of this by dipping into a fluid by displacement of that, then I will say that okay, what will be the, say if I have a sphere of the same volume, what will be its diameter. So, it is all basically the comparison of different one, but that property of that spherical particle and this particle will be entirely different. I am giving one example. Suppose if I have got 2-3 different particles like this, now when I have this type of shape, when they are flowing, they may be basically locked in between. So, they may behave like a bigger particle, but if I have a spherical particle, 3 spherical particles, they will have no chance of getting locked. So, your behavior could be entirely different. So, why should I accept that? So, but sometimes you want to use this type of definitions. Sphere of same weight, either you go by the volume or by the surface area or by the weight, and you are comparing with a sphere. Sphere of same volume, sphere of same surface area, sphere passing same sieve aperture, sphere having same sedimentation rate. Sedimentation rate means what is the settling velocity of that I will measure into a sedimentation pool, and then I will say that if I have a sphere of this density, what will be its sedimentation rate, then I will measure that size of that particle. So, like that there are many definitions, and so which definition you will use where and which one is accurate? No one is accurate, but we have to accept something. So, say suppose now my application is, if I am looking at your solid fluid interactions, probably I will use this definition because there the settling velocity is the most important thing. So, I have to look at the application. Suppose I want to know the size of this for selecting my screens, that what should be my screen apertures and all this, probably I will go for this, that is a sieve aperture. I will not go for this, then I have to go for that, because that I have to relate it with the process. Okay. Like that we have to decide which one will do. So, in summary, there is no such thing as a universal particle size, lots of definitions exist. That is why I said we are having moon mission, Mars mission and all sorts of technologies, but you look at the simple definition of particle size, we are still not sure. This is the difficulty with the particle technology. Be very clear which particle size has been measured in any data you are given. So, when you are looking at in a textbook or any journal article, they are saying that this is the size of the particle. You must know that what is the size they are referring to and what are the assumptions in that measurement. Then you will realize that what are the findings, whether they are convincing or not, then you can correlate the data, otherwise you may be misguided. Where possible, measure the particle size that matches your application. That is what I said. If it is solid fluid interaction, you go for that type of sedimentation based definition. For example, if you are designing a settling tank, like I have to design a solid liquid separation unit, like your thickener, then I have to go for that your definition, use the Stokes diameter like your sedimentation one. I will discuss later on. The Stokes diameter as measured by a sedimentation technique, I cannot use a sieve size for that. I should not. That what is the sieve size, equivalent sieve size. Okay. So, that is my basically the suggestion to you. Now, another thing I am coming very basic, particle shape. How do I define shape of a particle? You look at that, but particle shape affects flowability, that means at what rate it will flow, because you have to transport material from one place to another place, that is bulk material handling systems. Okay. So, many places, many engineering applications you need to transport material particles from one place to another place. It is not only related to mineral processing. Okay. Then packing density, shape means suppose I have to store 10,000 tons of material. It could be food grain, it could be some rocks, it could be anything. So, how much of volume I require? What should be my storage basin? And I want to protect it from say outside atmosphere. So, I have to design that. So, what should be the packing density I must know, because otherwise the what is the bulk density I do not know. So, I can't calculate what would be the volume requirement. I said only say actually it could be the 10,000 tons of material, but I have to know that. So, that shape dictates that what should be my volume requirement, because that is called the packing density, how closely they will be packed. Okay. Then particle fluid interactions. Same example I am giving, say suppose if I drop same mass, two particles, one is spherical, another one is flaky, which one settles faster? Sphere. Why? Because the flaky only change is in the shape. So, must be there is something with the shape. Okay. So, that we will discuss when we discuss about movement of solids and fluids. Okay. So, then your entire engineering system has to be changed, like any separation unit anywhere we are dealing with, I must have the idea of the shape. Okay. So, shape is more complicated to define and measure than even particle size. We have seen that how difficult it is to measure particle size, shape is more difficult. I will show you why. Now, if I have a spherical shape like this, very easy to measure the shape. So, what are the say actually no ambiguity about the size, I can say it is the diameter or the radius, and I can easily define the shape. Okay. So, if I have now you see apart from that, if I have a cylinder, cylindrical shape, it is a regular geometry. Now, the shape, how do I define the shape? Even what would be the size of that cylinder? What is the size of the cylinder? Can anyone define? It depends on its orientation. Now, if the cylinder is falling into my surface, that is suppose I want to deal with a system where it is falling in this direction, then its diameter is the basically the size, and if it is falling like this, then it is the length. So, I need to have the knowledge about the orientation of that, which is very, very difficult to predict. Okay. And then, so general description basically the cylinder also depend on different orientations, although I have got only two attributes, that is length and diameter. For this rectangle, I have three attributes to define A, B, C, that is you all know this. Then for cone, I have two. Now, I can, what will be the attributes for that shape? Irregular shape. Can I say A, B, C, D, E, F, anything? But this is what in naturally occurring mineral we face, that is irregular, non-geometric, not the say ideal geometric shape we encounter. How do I do it? Okay, so that is called irregular shape. We cannot name even. We cannot say it's a sphere or rectangle or triangle or anything we cannot give. So there, now how do I quantify then? Because for quantification is required for my modeling and optimization, and we are not dealing with single particle. I am again hammering that. So I need to have quick assessment of the shape profile. So for regular shaped objects, you have seen, other than your sphere, that we need at least 3 attributes: size, shape and orientations. But commonly used measures for size, I have summarized that it is equal volume sphere diameter, that I can represent it like this normally. For shape, there is a parameter, it is called sphericity. You see, these are all basically relative estimates or guesstimates, I would say. Sphericity defined as surface area of equal volume sphere divided by the surface area of that particle. How do I know the surface area of the particle? I have to measure. I have to measure the surface area of the particle. Even to know the shape, I have to measure the surface area of the particle. Examples. Some examples I am giving. The sphere, the sphericity is 1, the ratio will be 1. For cube, so this will be a good exercise, you just try, okay, with your geometry knowledge, and based on that definition, that whether these values are right or not. Okay. It will be a good exercise for your so this evening. Cube, it is 0.81. Cylinder, if the L by D is equal to 0.5, it becomes 0.825. If L by D is equal to 1, then this is that. L by D is equal to 2, then it is 0.832. L by D is equal to 10, this is 0.58. That means you see that even for a cylindrical shape, what is the L by D ratio? That tells you what is the sphericity of my particle. Okay? Please try it. So smaller the value of psi, greater the deviation from spherical shape. Now with this parameter, probably I can quantify, that is, if I say that it is a flaky particle, so that is basically, I would say, non-technical term. But you must say, sir, what is the sphericity of that? What is the value for that? Where from I will know? I have to measure the surface area, then only I can get to know. So I have to measure it. I cannot use my guesstimate that, okay, put a value of this. That is what I started with, that don't perform rituals, measure properties. If you want to fine tune your designs or you understand the mechanics, what is happening. Now orientation, what do I mean by orientation? Orientation means projected area or diameter of equal area circle. Now you see that in the high sphericity, that is your orientation, you orient it in any direction, you see that your sphericity, if I calculate, it will be very close to 1. This is called the high sphericity, although they are not spheres. That is how the qualitatively also some proposals have come into the literature, and based on these we can say that it is a very angular, subangular, subrounded, rounded, well rounded, like that we say it is a high sphericity, medium sphericity, low sphericity, like this. Now size, what are the units we use? You all know, but just for revision, we start with meter and we can go up to angstrom. Angstrom is 10 to the power minus 10. So these days the nanotechnology, many people are working, so they are dealing with this type of scales. But for this type of industry, mineral processing and coal processing, we don't go up to this range. Okay, we don't deal with much with this, other than our environmental problems. When we encounter environment related problems, sometimes we have to go to that sizes. Okay, otherwise we don't deal for processing purposes. So the most common designation is micrometers or microns. When very small in colloid region measured in nanometers when with electron microscope or by dynamic light scattering. Now, I am coming to the main thing, that is, so particle size, by measuring one particle size, does not give me any idea about the bulk material properties. There are many techniques to measure it, I will come back to that, but we are worried about the average behavior or general behavior of my bulk solids. So, for that it is not only the individual size, it is the distribution of that size. What do I mean by distribution? That is what I am going to explain here. Suppose I have got a mixture of this and then I have grouped them into different size range. Like say suppose I start with that these particles are greater than 1 millimeter. Now, then it is like a one sort of pie chart and I group them into one category and I say out of the total volume how much are they. So, we say this is 5%. So, that is up to 1 millimeter, greater than 1 millimeter. I am not giving any guarantee that whether I will have 10 millimeter or 100 millimeter or 1000 millimeter, I am not giving any guarantee. I am just saying that 5% of my total population is greater than 1 millimeter. Okay. Next one, I am saying it is up to 1 to half millimeter as 10%. So, I am giving a range, I am not specifying what is the individual size. Like that I am saying to half to 1/4 is 15%, 1/8 to 1/4 is 30%, then this is 50%, this is 40%, 1/8 to 1/16. So, looking at these numbers, what we can decide? Why? What is the need for this? Suppose my targeted material for a specific application, it could be anywhere, there I do not want these particles. Suppose I do not want these particles because these are basically too fine for me, I do not need that. Then I must know that if I am processing 1000 tons per hour, how much I have to separate out per hour. So, that is 40% of the 1000 ton. So, that means I have to separate 400 tons of that size material per hour. Now, I can decide what type of equipment, then what will be the scale of that operation, what will be the bulk material handling system, what is the capacity of that unit. So, how many numbers of that unit I require, as suppose it is water based process, how much of water is required, that depends on the process conditions of that equipment. So, that is how, so it is very, very important information I need to have if I want to design a process or maybe an equipment or even for selecting an equipment. Otherwise, my entire exercise will not have any meaning. Okay. Now, in that case also, what other information I will get? That, okay, now say suppose I say I give this example, say suppose, okay, I do not want this, but I want this for a specific purpose for this size, this fraction I want to sell it to Coal India, this fraction I want to sell it to maybe TCS, this fraction I want to sell it to some sand suppliers, this fraction I want to sell it to some other one. So, that means I have to discretize everything. Okay. So, how we are going to do that? So, in that case your decision will be that what will be my strategy? First, should I take this out from the assemblage of this because I have already removed it, or should I take this out and say let them be there, because in one go I cannot do it, I have to do it in stages. So, what will be the sequence of that operation? That depends again what are the options you are left with. So, this information I need to know at the very important one. So, particle size and other properties presents an additional problem they do not have single values. I cannot define a particle size of a entire mass of a heterogeneous system by a single value. That is what I will try to emphasize. Although, so maybe some of the students who have already taken a course on this subject may be saying that there is a size called D50, why you are saying we cannot quantify. I will come back to that, okay. So, as an alternative, there is a distribution of values of the property, and we require being able to define and describe these distributions. So, what do we mean by distributions? Now, what do I do? If I want to have your quantification of that is how do I plot them, how do I get a quantitative estimate of that? So, that data what I can do, I can go for a frequency plot, that is called a histogram type of plotting, that is particle size versus volume distributions. Okay. Then I can have a histogram that is called the differential distribution, because we have differentiated the different segment that is in the pie chart system. And the cumulative, yesterday I discussed the cumulative one. So, I can have a cumulative distribution of that, like the second example I have given, that I want everything but in a discrete manner. So, how much I have to do it? So, I have to have a cumulative distribution. So, I can plot them in a cumulative plot. That means, it is saying that if I have this particle size range, so that is cumulatively I will be having this is the volume percentage which is below this size and which is above this size. Okay? Clear? Now, I will come back to the very basics of statistics, because to understand this, you all know, but well, let us revisit it. Now, if I have a frequency plot like this, we can have the three different units we define, that is called the values. We call it the mean. Mean is the weighted average or the center of gravity. Then median is 50% point, mode is peak of the distribution. So, when I have this type of distribution, the mean, median and mode, they are all in the same place. But what do I mean by mean? Even the mean, you know, there are many definitions for mean. What mean you are talking about? So, there are other definitions also. I am just giving this type of definitions, that is, it could be represented by D10, what is 1 plus 2 plus 3 by 3, that suppose I have got 3 numbers, the mean could be 2. Okay. If it is basically D20, I can have a square root of 1 plus 4 plus 9 divided by 3 is 2.16. So, there are so many definitions, and none of the answers are wrong, and they have just been calculated using different techniques. So, when you look at any article, any book, if they are saying that mean value is this, you must try to understand that, try to explore that what mean they are talking about. Otherwise, your assessment of that, your article may be wrong. You know. So, most frequently we use this, that is called the volume mean diameter, which is basically represented by this formula. It is very easy, and I have already shown you that D43 means that is basically 1 plus 16, that is 1 to the power 4 plus 2 to the power 4 plus 3 to the power 4 divided by 1 to the power 3 plus 2 to the power 3 plus 3 to the power 3. Okay. That is the volume mean. Volume means is the volume is already in the cube root. Okay. Now, you look at, now if I have a distribution like this, then what will happen? My mean, median, mode will be at different places. Okay. So, this is slightly biased with the Court's size range, this type of distribution. And if I have a reverse one, that is, if this bias is towards this, we say that this is skewed towards the finer sizes, this is skewed towards the Court's sizes. I am not getting into that details. Okay. Now, there is another one, that is, I always said volume distribution. Now, there could be number distribution, there could be weight distribution. So, how I am defining the total say your assemblage of the particles? Is it by total volume percentage, mass percentage, by numbers, or what? I will give you this example that I must know that what distribution I am talking about. Suppose I have got these 3 particles and you have got as a radius is equal to 1 millimeter. So, and then the volume is basically the 4, then I can calculate what will be the V cube, that is 12. So, I can get the value of, say suppose it is 1 millimeter, this is 2 millimeter and this is 3 millimeter, and I have got this distribution. You are having 3 particles in each classes. Okay. So, I can calculate their volumes, okay, and then I can get their basically the volume distribution. So, total number of particles, if I have basically r is equal to 3 millimeter, then I have got 108 volume unit, because if I convert into volume, and then the total volume is 432. So, if I get the relative percentages of this by volume, you see this is only 2.8%, this is 22.2%, but this is 75%. So, this is the volume percentage, but number wise they are all 3, 1, 2, 3. So, the number distribution remains unchanged, there is no distribution, they are equally distributed, they are all 33.33%. But when I am plotting into volume distribution, they are entirely different. So, I must know what is that distribution. Is it the volume distribution or number distribution, mass distribution, what distribution? I will show you some more example. Does the mean match the process? Always. Does it remain constant with the process, the volume mean and number mean? Not always, I will show you. Particle size measurements often made to monitor a process like a size reduction. A size reduction in a crusher or a mill, I want to monitor that. I need to know that whether the distribution remains constant or not over a period of time, otherwise I have to interfere, I have to do something. So, does it remain constant? So, I am giving 2 examples, one where I am using it for size reduction, that is milling, and another one is size enlargement or size growth, that is agglomeration. And let me show you, that is whether the volume mean and number mean they change or change in which direction, which way. So, basically you say that this is the size reduction scenario. Suppose I have got a 100 micron particle, okay, breaks into 2 smaller particles. So, what will be the sizes for this? Equal sizes, it will be 79.4 micron each. Just do the calculation, it will be that. Okay. And I have got 10 into 1 micron particle, from where I have got this. Okay. And these are the 10 into 1 micron particles I am showing. Now, the size reduction as a number mean I am getting into that. That is, this one I have created 10 numbers, just 10 numbers of equal sizes. Okay. Now, you see that 10 particles of size 1, that is one of size 100 units, number mean is D10, you get 10 units. Okay. So, your number mean does not change, it matches with my guesstimate. Okay. A largest particle, that is 100, breaks into 2 of 79.37, because what I said that I have got 100 micron particle, I will break into 10 of 10 micron particles, so number is 10. But when I am going by the volume, it becomes 2 particles of 79.37 millimeter. So, it conserves volume by mass, so that is the calculation how we are getting 79.37. So, what happens to the number mean now when I am breaking it? So, it will be 10 into 1, that I have already have 10 particles of 1 micron size, plus 2 into 79.37, I have added them together, 10 into 1 micron particle and 279.37 micron particle. So, if I get the mean value, it will be 14.06 units. That is a basically increase of 40.6%, It was initially 10 units, because I have got 10 particles of 1 micron and I have added them with 1 particle of 100 micron. So, what will happen? So, the mean is the largest particle. So, here the number mean is 11 as 10 plus 100 divided by 11. So, 110 divided by 11 is 10 units. Okay. Now, when I have broken the largest one into 2 particles, the smaller particles remain unchanged, then what happens? Your this number mean changes, because 10 into 1 plus 2 into 79.37 divided by 12. So, it is 14.06. So, number mean has increased. Now, what happened to the volume mean? Okay. 10 particles of size 1, 1 of size 100 units. So, volume moment mean is D43, that formula I am using. So, I am getting this value, that is the 100 units. Okay. Now, largest particle breaks into 2 of 79.37, have broken 1. What happens to the D43? It becomes 79.37. So, now it is basically decreased. It was 100 when I have got 11 particles. When I have made 12 particles, the volume n has decreased. Okay. Now, let us see the, so can you see the problem? So, what is happening? Now, in this case, your number mean was 10, but when I have broken this bigger particle into 2, your number mean has increased, it is 14, and your volume mean was 100, but volume mean has decreased. Okay. Now, this is the size reduction process. Now, let me show you the same example if I go for size enlargement. You say that there is a size growth scenario. I have got 10 into 1 micron particle and I have got 10 46.4 micron particle. Okay. So, I have made them together to have a bigger size. This 10 into 1 micron particle remains identical. Now, see that what happens to the volume mean and number mean in this scenario. There is a size growth scenario. So, 10 particle of size 1 and 10 of size 46.42, we get a number mean of 23.71. Okay. 10 of 46.42 agglomerate into 1 of 100. So, does the mean increase? So, mean will be 10 units over a 50% decrease. So, your number mean decreases in case of your size agglomeration. What happens to volume mean? In the same process you can do that, and that is the volume mean here is 46.4 units, but what happens to the mean here when I am agglomerating? It is 100 units. So, summary is that it is number mean is equal to 10, but before agglomeration number mean was 24. Volume mean before agglomeration was 46, volume mean is now 100. So, now it is increasing volume mean, number mean decreases, but in case of size reduction it is just the opposite. Now, we can get into mathematical domain to explain it mathematical that why it happens. I am just giving an example, but if someone is really interested in doing mathematical analysis, can come out with this analysis that why it happens, that why the means they change with the process, that whether it is agglomeration or it is size reduction. Okay. That I leave it to you. So, my message is therefore analyze whole size distribution, not mean alone. So, do not get only D50 value, it does not give you the actual picture. Measure the entire size distribution, that is what I want to stress, because otherwise you do not know that whether the mean is changing in which direction and what mean you are talking about. So, better to have the total size distribution data. Okay. Now, how do I measure this? The particle size analysis, and even this particle size analysis data, they differ based on the technique you have used. That is what the properties, that is how do I measure the size, that is what I said. So, same principle we are using to measure the particle size distribution, similar type of properties. So, that is PSA stands for particle size analysis. So, why should one consider various methods of particle size analysis? Why not always we do sieve analysis as the easiest, but many times it may not serve your purpose. There are some limitations, and I must know what size distribution I am talking about. Material suppliers and users employ many different types of instruments depending upon their budget, depending upon their requirement, depending upon the influence by the marketing people. They are convinced, but that may not be adequate system for them. Use a different technique to get a different answer. So, if you use different technique, your size distribution remains same for a material. You are not changing the material properties, but you change the technique of measuring size distribution, you get different numbers, different answers to the same question. How can it be? So, that means I must know what is the basic scientific approach behind that measurement technique, and then what are the likely errors associated into that, and which one I should accept. That also depends on what are my application domain. Okay. It is important to understand how analysis methods differ in order to know how to compare data. I give this example. Suppose I have given you a blasted rock, or maybe I am giving you a particle size starting from 1 meter to 1 nanometer. Everything is there. I ask you to give me the size distribution. Can you do sieving? Can you do sieving for 1 meter particle? No. Can I do sieving for 1 nanometer particle? No. So, I have to use different techniques, but I have to have the size distribution card, only one single size distribution card. So, how do I correlate the different techniques? And if you want to do that, you will find that you cannot get a curve. So, I must need some correction factors. So, where from I will get those correction factors, what is the basis? So, I have to understand what size they have actually measured, okay? And then how do I convert from some measures the volume percentage, some measures weight percentage. So, how do I convert this? That is what I said, that is you can convert it like this. So, you should be very familiar with the size distribution techniques and the conversion of the different techniques. Okay. Now, size range by technique, you know, normally the same question I am coming from 1 meter to 1 nanometer, that I am trying to answer it here. Like normally 1 meter you can measure it by some other bigger screens, you know. I don't bring 1 meter diameter particle into a lab, I do it in the plant site only. Okay. So, I can have some kind of the gigantic screens to identify them. Normally when you talk about, like we start with say suppose 1 millimeter or maybe more than that. So, you can easily do the sieve analysis. I will show you what is sieve analysis. Okay. And when I am going to the finer size ranges, that is sedimentation and centrifugal analysis by using centrifugal forces, you can do that. Then there are acoustic spectroscopy methods up to 100 micron, optical microscopy, image analysis method, electrical conductivity method, so on. But most popular these days is the laser diffraction, because it can cover the entire size, most of the size range. Okay. If some of you are interested to see that what is the laser diffraction unit particle size analyzer, you can come to my lab, I will show you, okay, how does it look like and how it works. And that girl who was here, who was taking attendance and all this, she is basically working on that. She helps me in getting the particle size analysis data. Now, when I have got all these different techniques, now say suppose I send a sample to 10 different labs and they are using 10 different techniques like this, and I am getting the data, I will be confused. Now, how do I compare the data? That is my problem. Then I have to know what is the technique they have used, what are the correlation between each one, then I have to have a conversion to that. Otherwise, I may not get to know what is the actual size distribution. Now, general principle I am telling you, some of these most important one, laser diffraction, what it measures? It measures basically the equivalent spherical diameter. and then it counts per unit volume that how much are there. Okay. Dynamic light scattering, they measure hydrodynamic radius. Image analysis, basically lengths, widths, equivalent spherical geometry, the dimensions. Acoustic spectroscopy, it measures equivalent spherical diameter, like that. So, some of the most common methods, because our entire course is focused to mineral and coal processing. If you are say dealing with nano sizes and all this, you cannot use sieve analysis. So, I must know that I am learning, I am doing this particle characterization, what are my application domain. So, we are rather using much of working on a macro scale than in a micro scale, although we say that these are micrometers, but in terms of particle size, handling difficulties and all this is a macro scale. Okay. So, some of the more common methods what we adapt, that is basically sieve analysis, that is most frequently used in our industry. Sometimes for very fine particle processing we use laser diffraction methods, then these are the methods which are available, but I do not think most of the mineral processing laboratories, they either use sieve analysis or laser diffraction or maybe combination of this. In most of the cases, the plant people in their laboratory, they also use this, but for on stream analysis and other, say for controlling the your process, they are now using image analysis based systems. Okay. There are some say professional versions are available, but I am not going to mention here because I cannot market their softwares and techniques. Okay. So, sieve analysis, you may think that it is very easy one. How many of you have done sieve analysis so far? Please raise your hand. Okay. Okay. Now, my first question to you all, that is, I have given you a 1 kilogram sample. Okay. You want to do sieve analysis. How do I select the topmost sieve and the bottommost sieve? How do you select? Can anyone answer? How do I start it? Because sieve analysis means, that is, I will have sieves of different apertures and then I will put them into a stack like this from the coarsest to finest in some series. My question is, how do I select the topmost and the bottommost sieve? I have no idea about the background of that material. What is the criteria for that? I will answer it. If you do not know, I will answer it. Okay. So, let me first explain it. So, sieve analysis is one of the oldest methods of size analysis and still it is being practiced frequently in mineral processing industry. It is accomplished by passing a known weight of sample material successively through finer sieves and weighing the amount collected on each sieve to determine the percentage weight in each size fraction. What does it mean? That means I have got a stack of sieve of different apertures. I pour my material onto the topmost sieve, that is the coarsest to finest, that is the order. Then it is called some kind of sieve shaker, that shakes, and then you allow it to pass through the apertures if it is finer than that for a certain duration, and after that you stop the machine, you take out each sieve and say transfer all the materials whatever is there into a weighing balance, you take the weight, take note of weight, and then you note down that how much of sample were retained on each sieve, and then you go for that. So, that is the initial size distribution, your pie chart I have shown. So, that data you can generate out of this basically the test. Okay. That for, say suppose I have started with 1 kilogram of material, after 10 minutes when I have stopped the machine, then I will take it out and then each one you see that there is a range, because I say that these particles, this much of particle has passed through the aperture of this screen, but they were retained on this. It is like the yesterday I say I should discuss about the sink floor, the same thing, that it is finer than this sieve, but coarser than this sieve, like that we do it. Okay. So, it can be carried out with wet or dry materials, and the sieves are usually agitated to expose all the particles to the openings. Okay. So, different mesh screens are used to measure particle size. What is the mesh? MESH. As a number of openings per linear inch. Many people they say it's a per square inch. No, it's a per linear inch. Okay, I'll come back to that. Now, our interest is the particle size distribution, and there are different standards of sieve manufacturing companies. There are different standards you have to maintain for the sieves. Why these standards are required, that I will explain. Okay. So, this is called one kind of basically sieve shaker, it is called row tap sieve shaker. You see that these are the screen surfaces, the dimensions could be different, the screen apertures could be like this, these are basically oven wares. That means you have got very fine strings like this could be also a screen surface, but that is basically the regular your square holes are there, it is like your screen surface, and then you see that each hole are of equal dimensions. But in between, there is a good example of that, in between there is some width is required, that is the wire thickness. So, suppose if I have got wires, oven wires put together, so I must give some space for the wire thickness. So, when I am saying that say suppose 40 mesh, so in 1 linear inch I have got 40 equal aperture, but what will be the dimension of each aperture, that will depend on what is the thickness of my wire. So, that thickness of the wire varies from manufacturer to manufacturer. That is why there is a confusion. So, people have come out with some standards, ASTM standards, that is the American standard, they follow certain standard that my wire thickness will be this. DIN standard, that is the say German standard, they call it, they will have a different wire thickness. Similarly, the different standards they have a different wire thickness, and that changes your aperture size, because how much is this area, that is where my aperture is not there. So, that will decide that in per linear inch, if I have 40 equal holes, what will be the dimensions of each hole, that depends on that. So, that is the wire thickness I must need to know. And the sieve hole sizes, the shape could be different, typically, okay, so it is not required. Now, this is what I am saying, that is the test sieves, the apertures. Okay. So, these are the wire area, that is the how much is the wire thickness, that varies from different standards. So, I must know what are the standard, and then when I am using a sieve analysis, please do not mix up sieves from different standards. If I am using a ASTM standard, you select all the sieves of ASTM standard, that is written on top of that, on side of that sieves. Otherwise, again you have a different problem in plotting, in getting the distribution, because the thicknesses are different. So, you are not having a sequence, I will get to that, I will explain you that. So, these are basically the different test sieves are designated by the nominal aperture size, which is the nominal central separation of opposite sides of a square aperture or the nominal diameter of a round aperture. So, that is basically the dimension, that is of the your maximum aperture for this type of geometry, or this is the diameter geometry. Because why you need to do that? Because if my particle, when it is falling, if it is falling in that direction, then it may pass through the maximum dimension of that. So, what is the minimum dimension or maximum dimension? I am talking about that aperture when it is not spherical, that is also very important to know. Okay. Now, these are basically the some pictures of that. Now, how do I know what is the mesh? Okay. What is the opening area? So, my sieving, I must know that how much is the opening area, and that is very, very important for industrial screening operations. Suppose I have separated, I know that I want to separate that previous example, I want to separate 100 micron particles from my assemblies. Now, can I use a screen? Now, for that maybe. So, what type of screen apertures I require, how much of surface area I require to handle that much of material, that depends on how much of surface area I am available with. So, the available aperture per unit area of screen is the most important criteria of screens. The apertures may be determined if the diameters of the weft and wires are known. Weft means that is the your longitude, that is your horizontal, that is your vertically what is basically laid, that is the wire, and what is basically in horizontal direction, that is called warp. Okay. So, the opening area per unit per linear inch will be A0 will be LA. LA is basically the aperture, each aperture how much is that, and then A0 is the open area expressed as percentage and dW is the diameter of wire. So, what is the relative opening per unit say length? So, it will be LA by LA plus dW whole square, because the how much is the surface area it is now covering. So, what will be my opening area for my particles, that means how much of surface area I have to select, what will be my screen dimensions, that I can calculate based on that. Now, if it is having this type of rectangular, say suppose this is not rectangular what I am showing, but if it is rectangular, if I assume, then the formula will be just simply I have to convert it with the length and width. Here I can take one dimension, I have to take only the width and the in the horizontal wires and all as well as the vertical wires. I have to take the thicknesses of these two. Is it clear? So, that is how we get the area. Now, I will give you the basically the example of this. Suppose this is my 5 mesh. I am saying that many places you will see that screens are basically designated at mesh sizes. So, 5 mesh means suppose this is 1 inch, 1 linear inch, I have got 5 equal holes. Okay. So, now this is the wire. So, I have got the wire thickness. So, mesh number is equal to the number of wires per inch or the number of square apertures per inch. So, I have to calculate that what will be the basically the average size of the aperture, each aperture size is how much. So, the mesh of a screen is defined by the relation M is equal to LA 1 by LA plus dW, that is the thickness of that I have to take, how many apertures are there, and for measurements in inches, if I want to convert it into millimeters, then it must be multiplied by 25.4. Okay. I can give you a small exercise to calculate the mesh size of a screen. Okay. So, maybe tomorrow or maybe in second half I will bring that. So, mesh size of square opening, I can just get into that, M is equal to 25.4 S square, A0 divided by 100 L square. If I put the value into the previous equation, I will simply get that. Please do practice on this, that is how do I do the conversion and all this, because we have to cover many things, so I cannot slow down the space. Okay. But I am giving you the information, these are very basic things you can calculate, but you must have basic understanding of this. So, these are the conversions between mesh and microns based on different screens. Okay. Now, I will now answer some of the questions, very practical questions, that is what I asked. That is, suppose I have got a 1 kilogram of material, how do I select the topmost sieve and the bottommost sieve? The answer is you have to first do trial and error. You have to have some guesswork. Okay. You take only one sieve, say suppose you have 5 millimeter, and you pour entire material into that, just sieve it with your hand, and if you see that total material retained on the sieve is not more than 5% of your total population, not more than 5%. That means, if I have 1 kilogram, 5% of that is 50 grams. So, I should not have more than 50 grams of material retained on the top sieve. If it is less than that, you say okay, that is my starting sieve. Similarly, for the finest one, you also take another finer sieve, and your passing sizes, how much is the material passed through that material, that should not be more than 5%. So, now I got the topmost and bottommost sieve. Now, there are different standard wise, the standard why I said that ASTM, DIN and all this, there are basically the different series of screens are also there. That is, if I start with 1 millimeters sieve, what will be the next dimension? Next sieve will be what? I cannot say arbitrarily. The next one will be 0.8, then next one will be 0.6, next one will be 0.2. If I ask anyone, you will all say some random numbers. But there must be some standard procedures and there must be some reasons behind it. So, what we are trying to do, we are trying to have a equal distribution. I want to have a distribution curve to be plotted. So, for that what we do is normally the area is a function of your square. So, what you do that if I first sieve is 1 millimeter, you go for a root 2 series. What is root 2? 1.414. So, you divide 1 millimeter by 1.414, the next sieve will be of that millimeter. Then divide it again root 2. So, that is called the root 2 series. So, that means when I am plotting it, the area will be squared, surface area will be squared. So, I will get a good distribution, because that is my major aim for a size distribution. Like that, if I want more precise, more close information, I can use a fourth root of 2 series. Even you can use a 10th root of 10 series also. So, that is the thing I have to know, that what is the series, what is that standard procedure, how do I select my sieves. Now, you cannot mix up this again. I cannot have first 2 based on root 2 series, next 2 on 10th root of 10 series, then next 2 by 4th root of 2 series, you must maintain. And you must have some kind of your justification, because more number of sieves you are using, the more amount of time and your money you are spending. So, whether you need that type of information, that is also very important. So, what for I am doing this particle size distribution, what is my objective, that also I must be very clear. Okay. So, thank you for the first session.